In this video, we're establishing a generalized rule for all of you, a indeterminate power type rule, and you should know this. The limit rule that you should know is this: limit as x approaches 0 from the right. A one-sided limit, your function would look something like this, which is being evaluated in terms of the limit f of x to the power of f of x. And you know, you're looking at two functions which are similar, they're identical actually, the output should always be a 1. This right here is a good generalized rule you should know. A good example would be where f of x is equal to x. You can do it for sine x, you can do it for tan x, you can do it for hyperbolic sine x. What's the commonality in all of these? In all of those functions, f of 0 is always equal to 0. Put 0 in places of x, your output is always 0 for any of these functions. And this is what you're looking at. And why is this important? Because when you have this type of a condition, you end up getting an indeterminate power type 0 to 0, which you know you can convert into an indeterminate product type like this. And you know, for this, positive and minus infinity are equivalent. Then you can convert it into a quotient form, 0 over 0, or infinities positive or minus. That's what you have. But this right here is your general limit rule. You should know this condition, right-sided, and how would you prove it to be true? You can. Natural log y is equal to f of x and natural log f of x. You've brought in the properties of logs. When you put zeros in here, you're looking at an indeterminate product type. And then you know you can do the L'Hopital's rule and convert it into a quotient form. You're looking at the derivative of the numerator by means of either this f over 1 over g, or you're looking at g over 1 over f. But in this instance, f and g functions are identical. They're actually equal to each other. So you can look at the derivative of the numerator, d over du, L and u, and then du over dx, the derivative of your function f of x, divided by the derivative of the reciprocal of your function 1 over f of x. And then you could put 0 in places and determine if the indeterminate limit form such as this still exists. When you run this through, you're getting a derivative of your f function divided by u, which is the derivative of L and u. Here you can do the quotient rule. 1 over f of x is going to be minus f prime over f square. You can run this through quotient rule, you'll get that exact output. F prime divided by u substitution coming back in, which is your f function, times f squared divided by minus f prime. F primes here indicate the derivative. This cancels out, that cancels out, that cancels out, that. The only thing which remains is minus f, and then you can bring in the x and then 0. You're looking here minus f of 0, and you know your output here is a 0. But that's natural log y is equal to 0. Natural log y is equal to 0. Y is equal to e to the power 0, which is equal to 1. And that's what you're seeing right here. This limit rule over here works. F of x to the power of f of x, looking at values of x approaching 0 from the right for these type of functions, x, sin x, tan x, sin hx, you'll always have an output 1. You can run values such as this, like 0.001 on the DEG mode and run it through sin x, tan x, and hyperbolic sin x. You can even do 0.001 and run it through this. You'll have something like 0.001 to the power of 0.001, and that's just you looking at this function. You'll see your value is here getting close to 1 as these values become increasingly closer to 0. But you can run this through on your own and prove this to be true. This limit rule over here is general, but it's true. Have a good day. Bye.